Felix, for a nice introduction. Today's talk is everything but directions and all the other awesome and exciting things you can do with routing besides going from A to B. So what we're looking at is a bit more complicated than A to B. So today's agenda, I'm going to give you a brief overview, omitting all the technical details, of what is called route labeling algorithms. I put route in brackets. At first I had their labeling only, but I don't want to confuse that with map labeling in terms of rendering, but we will see what route labeling algorithms are. We're going to look at 3 examples of what we can solve with them. Then we're going to dive in what's going to be a really nice application, namely vandalism detection. So let's get started with route labeling algorithms. The intuitive approach to routing, to give you an idea, is whenever you go from A to B, and A to B are sufficiently far away, you will almost always enter the arterial network at some point. And the second idea is, for a fixed location, the routes to almost everywhere lead over a very few but very important locations in the road network. Let me give you an example. This is Karlsruhe, and this slide is from a previous life in academia where we were located on the opposite side of the park. And we told people, well, look, wherever you want to go in Europe, and if it's far away, you can cover all these paths by like 3 locations in the road network, which are very important junctions. So we are where the blue flag is, and then the 3 locations given by these skewed squares, and you see that all paths to far away can be covered by very few but very important pieces of the road network. So to give you more insight, what we currently do in OSRM is that we pre-process the road network. So what we do is we take the input data and we discover layers of importance. We do this automatically, not necessarily based on functional road classes like highways, like national roads, stuff like that, that administration says is important. But we look at the topology and infer importance by a measure that's close to how many paths lead over this or that piece of road. And once we have this information, we add additional structure to the data. And we leverage that for fast queries. You can think of it as a climber layering on pieces of structure from one piece to the next. And the way we construct this is that the amount of data that you have to look at to find a route is relatively small. So for example, in a road network with the hundreds of millions of pieces of road, we only have to look at a couple hundred pieces to actually infer where the optimal path is going, because we know all these important places in the road network, like I showed you before in the previous slide, where you can cover all the important paths to far away with only very few but very important pieces of road. What we have to do is we have to search simultaneously, and this is where the phrase labeling comes in. We search simultaneously from the source and the destination from A to B, and what we do is we search the way up. We only look at more important pieces of road. And what the math behind all this guarantees is that we will find one piece of road from both sides that's somewhere in between that we label with the correct distance. And the correct distance means how far is it away from the source in the forward way direction, and how far is it away from the destination in a reverse way. And once we have this one piece that we reach by both ends, we can infer not only how far is it away, how long does it take, we can also in a very recursive way discover how the path actually leads, what's the geometry of it is. To give you a sketch, we see the source here, target here. We explore the ever more important pieces in some sense only going up, and then we find some piece that we reach by both sides that's in the intersection. And compared to the overall size of the road network, what we have to look at is small. So just keep in mind it's small. Also note, what we have to explore in terms of more important pieces of road is for a given location is always the same. So if I go from Karlsruhe to Rome, what I have to look at in the forward way is always the same, even if I go to Copenhagen. So this is very abstract, but very important to keep in mind. Let me give you the nutshell. So what we look at when searching for a path is only a small subset of data. We go up in forward direction from the source, in backward direction from the target. And we reduce pathfinding to something that is like a set intersection. So what we're looking for is this piece of road network or pieces of road network that we find in the intersection. And that's all we're going to need to put that into more complex applications. Also keep in mind, exploring these pieces, these search spaces, is super fast. It's like a millisecond, maybe 3 milliseconds, but then we're going from East Coast to West Coast, like a really continental route of thousands and thousands of kilometers. So what we're looking at, closest dispatch. What is closest dispatch? Well, it's a bit like this. So you've got a couple of guys on patrol. You've got the yellow guy that we call an incident, and every now and then one of these guys on patrol is dispatched to the location of the guy on the incident. That's the incident. So think of it as we have multiple vehicles on patrol, perhaps taxis circling the city looking for next customer. Perhaps it's the police on patrol in cars, bikes, perhaps on foot. So there are a couple of examples from the real world. And at one point, an incident comes in. Someone calls for a cab. Someone reports a robbery. And naturally, we want to alert the one vehicle or the one person on patrol that is the nearest one to response. So essentially what we're looking at is what we call a many-to-one path problem. So we have many guys on patrol, we have one incident, and what we like to infer is what is the closest of the many to the one location. We're speaking of network distance here, because let me give you an example. This is Karlsruhe. We're somewhere over on the right-hand side. This is like 15, 20 minutes away from here. So assume that the green guy is your vehicle on patrol and the red guy is the incident. You don't want to do cross-slice distance, because although these two are only 200 meters apart from each other, it takes like 30 minutes, 45 minutes to reach them. So what we want to look at is network distance. How long does it take in the road network to reach the one person? Also, we have to cross the bridge here, and if you're local, you know that's usually clogged by a traffic jam. So what we do is think of search spaces. We know we have to do somehow on the target search up, on the source search up. So what we do is for each source that we have, for each vehicle on patrol, it reports back its location every now and then, let's say every 5 seconds, every 10 seconds, perhaps even every second. exploring the search space is fast, like a millisecond. So we can update like 10 times a second and don't even have a problem with computational time. So for, let's say, a responder, we explore the search space. We have 1, we have 2, we have 3, 4, 5. We store that as preprocessed data. And we update that because we have many more location updates than incidents. And now an incident comes in. Someone reports a robbery. On the telephone, the person calling gives a location. And what we know is, okay, we have a location. Now, the incident is going to be our target. And as we reduce pathfinding to set intersection, which is a super easy solvable problem that is taught to 6th graders in math, we can solve that easily by just exploring this one target search space from the target in reverse fashion and do a set intersection and note the one responder that is nearest. And once we have that, we can infer a path and alert responder number 2 and say, well, listen, you're the closest one, please respond to the incident. So what we do is, we do a set intersection with the preprocessed data that we update every now and then, perhaps in a regular fashion, and get the best responder. And the next application that we can do is walkability. We want to look at how walkable is a given location. How easy is it to conduct the necessities of daily life, for example, by foot or by bike? So we have a given location, and we want to know what is the nearest pub. How many pubs do I have in this or that distance? What's the distance of the nearest grocery store? How far is the doctor away, a dentist, and so on and so forth. If you have kids, how far is the kindergarten away? All this is important if you're looking for, let's say, a new apartment, right? And for example, in the US, there's a company called WalkScore that computes a score for a given location. And this is really important for real estate agents because they can put up in the ad for an apartment, say, well, we have a walk score of 89 of 100, which is supposed to be good or bad, depending on what you're looking for. And it gives you an idea how well connected this one spot is. Looking at it from a route planning perspective, we say, well, it's essentially, this is a one-to-many problem. We have one location that's perhaps the apartment that we're looking at, and we have plenty and plenty of targets, which is all the pubs in the city, all the doctors in the city, all the kindergartens, right? And summing up, we have many fixed locations, which are our targets, our points of interest, our pubs, our bars, grocery stores. We have one query location, that's a source, right? That's the apartment in question. And what we do is, essentially what we have done before, but only the other way around, we do a simple pre-processing, and we say, well, for each target, we pre-process the reverse search and store that. Usually, this is like 2 kilobytes, 4 kilobytes per given location. And this is all very doable and doesn't take up too much RAM. And then we can do fast set intersection. So for each of the points of interest, we do the reverse search because for every location that we're going to query, we would repeat all these searches again, so we just store them. And points of interest just don't go away on a daily basis. So if a bar opens, it's going to stay. So it's not like you get updates every 5 seconds for point of interest. And even if you could, I mean, these search space explorations are fast, so you could update that in real time. And now, when we get a query location, we retrieve one forward search space and intersect that with the aggregated data. This is just traversing a list, so it's super fast. So in terms of query time, we're talking about like 2 milliseconds retrieving a very complex storing function for a given location. So no need to store that in the database, the value for each location, but we can retrieve that on the fly. So what we do is, we do a forward search, intersect. It's the same game as before, only the other way around, right? Let me give you a more visual example. We tested that on a data set for San Francisco and produced the seat map. The red locations, colored locations, are very walkable. If you look at the top right corner, that's the most touristy area of San Francisco. And of course, there are lots of stalls, there are lots of shops, there are lots of amenities that you'd like to visit, which makes it a very walkable, very easy location to live if you want to do all the daily things by foot. If you look more here on the western side, you see the green, bluish area, and that's a residential neighborhood. It has an important street in the middle, somewhere here, where you can see a couple of orange or red spots. And that's a street where you have shops, right? And if you're looking for things you can do by foot, you want to stay close to the areas where you have all the amenities, right? So if you move into this neighborhood, you shouldn't be surprised that you at least need a bike. Which brings me to the next example, and this is distance tables. Distance tables are the major building block for essentially every logistics optimization. What you start with is a distance table. You're given a set of source and target locations, and you want to come up with the table that computes all the pairwise distances, right? And we know, well, we have fast routing, so we could just do a quadratic number of location lookups here. But this is not the smartest thing that we could do. We can be much faster. We can be faster by significant amount. So essentially, this boils down to a many-to, oh, sorry, that's a typo. It's supposed to be many-to-many path problem. We have many sources, many target locations. So solving that in the same modeling that we had before is very easy. So for each given target location, we pre-process the reverse search spaces and put that away in memory just to pick it up. And then we take each source location and intersect each source location with, we take a source, intersect that with the pre-processed data that we would repeat every time we would compute one of these quadratic numbers of pairwise distances, so we just keep that. And instead of computing one number at a time, we can compute entire rows or columns at a time, right? So because what we know is we have one source and many locations, target locations, so we can just fill out the entire column at once. So it's something like a repeated many-to-one problem. And the search complexity becomes linear. So instead of, if we have like 100 locations and want to have the pairwise distances, we don't have to do like 10,000 lookups anymore, but we have to do 200, right? 100 for the target locations, 100 for the source locations. And this is an entire different ballpark. We can use that for vandalism detection, right? How would we do that? Well, with vandalism detection, what the goal is to somehow filter out automatically issues in the data by looking at changes. For example, by looking at each change set individually, or by, say, we pre-process our routing database every couple of hours, and then we look at differences between the one data set and the other data set. And we want to, here we want to detect vandalism in the road network. So the important thing to notice here is vandalism in the road network becomes important if it is on very important roads. So if you delete a major highway, it's going to impact many, many locations. If you delete a minor road, well, it's going to impact essentially no one. So what we're looking for is, where is there significant vandalism happening? This is not actually a problem in OpenStreetMap. We have very limited vandalism, and usually stuff gets fixed fast. But in case someone asks, we may want to have some system in place that checks periodically, is our data going bad, or is it still good? So remember what I said before, the roads to almost everywhere, they lead over a few but very limited number of locations in the road network. We can exploit that. As I said before, removing an important street will have an impact on many origin and destinations, and even on randomly selected locations. From a math point of view, this is very important because you can pick locations automatically at random, and it's not easy for an adversary to vandalize around these selected locations. So what we want to do is, we want to cover the most important roads and look for significant changes. So what we do is, we select a good set of locations, and from the pre-processing of the routing that we do in OSRM, we can infer the, say, top 5% of most important pieces of road very easily. It's just a byproduct that at some point during the pre-processing, we just need to write out to disk. So that's very easy, that's very cheap. What we do is, we compute distance tables. We compute distance tables on several levels of the hierarchy. So we can cover metropolitan areas. So for example, we select like 100 locations that we deem important for the Karlsruhe area. We can do that the same way for Paris, for London, for New York. We can do this for the federal state of Baden-Württemberg, where Karlsruhe is located. We can do this for the state of Texas. We can do this for entire countries. We can do this for continents. The properties of the road networks allow us to, depending on the area that we're covering, always select the most important points. It's very easy. So what we do is, we compute a distance table, and we store this distance table. And then when we reprocess all our routing data, we reproduce the distance table and look for significant changes. Because what we know is, oh, there are very few but very important roads that we want to cover. And whenever there's an issue, it will pop up in these distance values. And what we do is, we just look at differences. So we will have some threshold for significance, because if there's opening of a new road, for example, driving times may change, but we don't expect that to be super significant, and even if it is, we look into the change and see, well, it's a good one. What we're looking for is something like this, where we have a route, let's say, from Frankfurt to Munich, and someone just went nuts in the editor and pushed the routes in a zigzag way. This used to happen more. It happens less now, which is nice and usually is fixed within minutes. But if it's happened on a smaller scale, we can detect that. If it's happening on a bigger scale, because of the hierarchical properties of the road network, we can just easily detect that. That's very easy. We have a prototype system of that running internally. We are very positive to have something more visual for you to see in the coming weeks and months. And we are actively working on monitoring the road network. And at one point, we want to do that in real time. Like, we have a change, and 5 minutes later, we have a decision. Is any of these changes that occurred within a few minutes, is any of that vandalism? Is that significant? Is that something we have to look at? Yes or no? Right. Which is going to conclude my talk. So if you have questions, happy to answer.
If you have questions, please raise your hand so I can come to you with the microphone.
With your last word, you are telling you are building, you can do update of OSRM data with diff?
Sorry, I only got half of that.
Sorry. Can you update OSRM data with diff?
Not yet.
Not yet. But
The emphasis is on not yet.
Okay.
More questions?
An important application would be, for example, a routed search for points of interest. And I don't know any OpenStreetMap tool for mobile which can do that now. Are you offering any interface to deliver such a service?
Well, we do have a public API that you can query over the network. We don't have a truly offline solution yet, but if you have internet connectivity, you can query the API and get information from there.
Okay.
Hi, you talked about layers of importance and how you compute them.
Yeah.
Have you looked into using GPS traces to enrich that and maybe modify that?
The thing is that road networks are in some way benevolent, so they behave nicely. You don't actually need GPS trace data to infer importance, but you can infer, let's say, some level of importance, the number of shortest path or optimal paths that a piece of road carries. You can infer that if you have, let's say, something like expected travel time. So what you can do with trace data is look at how good are my estimates, right? How compared to real life. You would go with that, but putting that into the pre-processing itself is a bit of overkill because the results that you get are not significantly different.
Second question, maybe.
Yeah.
Would this be adaptable to other types of routing, for example, cycling or walking?
Yes. So the properties that we exploit, among others, are hierarchy. So you have a very strong hierarchy if you look at cars. So you have the arterial network that's like less than 1% of all the roads, but carries 99.9% of all the traffic. This is a bit less true for biking, but still true enough to make it work. So we are going to have something for that too in the future.
To continue a question about GPS traces,
yeah.
It could be important for detection of turn restrictions because on the map there's not every turn restriction is mapped.
Yeah.
And you could detect which turn restriction is there and some additional data to the road network.
Yeah, this is very true. We only have a very limited number of turn restrictions mapped. That's like 250,000 for the entire planet right now. That's not too much, because 250,000 is easily true for the southern half of Germany. But we want to have a more complete coverage. So inferring something like turn costs or more general turn restrictions from GPS data is feasible, but you have to be careful what you do. You have to look at how important are all these adjacent streets. For example, if you have a turn restriction in an urban area, and more or less all roads that are next to the restrictions are equally important, right? And there you can infer, well, only 1% of the people that I trace make a left turn, so it's probably forbidden, right? If you look at at a highway, an arrest station, a gas station, 99.5% of the traffic will go straight, right? And only 0.5% will make a right turn. So you have to have a solid modeling to detect what you're looking for. But I'm happy to talk about more about that offline. There's something in the works.
How do you handle parameters such as like avoid toll roads or maybe even real-time parameters like current traffic from an external source?
All right. At the moment we don't, but we will. This is
You can give us an idea how you technically do this, because I understand you do pre-processing on those parameters.
Right. Yeah. So from technical point of view, it's pretty clear how to do that. There's a prototype running doing that. It's not yet production quality. It still needs work before it gets released.
Any hint how you do that? How technically how you solve it?
Graph petitioning is the name of the game. Happy to answer more of that offline.
Okay.
Just ping me somewhere and I'll tell you how to do it.
That you're working on it.
Yeah, I'm working on it. Yeah, sure.
Just quickly going back to GPS traces, I am actually doing GPS trace analysis with OSRM. I'm not doing a talk on it, but you can talk to me later about it or something.
Okay, thank you very much. Thank you, Dennis.
Thank you. Sorry to hijack that. One quick announcement. For the past 2 days, we have Windows support now, and we invite everyone to download the latest build. Use that on Windows and report your experiences. This is really fresh. This landed 2 days ago in the development branch. Thank you.